This is part 2 of waves. Just a brief recap of what happened in part 1. I went over some of the characteristics of light waves, how light is like a particle, how it's also like a wave, and how sound is only like a wave. So light is a little something different. If sound hits you, it's not the sound itself, it's the sound energy causing some other material, like some water in a pool or some air, that's hitting you. Now, if you're in empty space and light hits you, there's nothing else around. It is actually the light that's hitting you. So light packs a punch. Sound really doesn't. It only packs a punch if it's moving through something. I was saying that light is it's part of what's called an electromagnetic radiation. There are all kinds of radiation. If you took a green light wave and you scrunched it together, then you could turn it into a gamma ray. It's just the only difference between green light and gamma rays is that the gamma rays are much higher energy and squished together. And this actually does happen in space when you have stars moving one direction or another. The light in front of them can get scrunched up, the light behind gets stretched out, and that's called the Doppler effect, and we won't really talk about that much here. There's a red end of the spectrum, a blue end of the spectrum. Red is longer wavelength, blue is shorter wavelength. Mentioned that hot stars are blue, cool stars are red. The kinds of radiation that are most dangerous are the short wavelength radiation because they have high frequencies, and that means they have really high energy. Light can reflect, it can curve and refract, which we're going to get to soon, and it can also scatter. And the scattering is what does things like causes blue skies. Sunlight travels through our sky. The bluish looking short wavelength visible light bounces all around. So that's what we see when we look all over at our sky. The other colors, the longer wavelengths, when we look at the sun, those make it straight through. So that's what we see when we look at the sun. Now, next part. The last question was why is the sky blue? And now the question is, why are sunsets red? So this was the moon, remember? This was the blue sky, and there's a red sunset. So in the scattering can explain this too. Put this back in position. So first we're going to do what this says. One of the drawings on the right shows a person looking at the sun at noon. The other shows a person looking at the sun at sunset. Label the drawings to show sunset and noon. You should be able to figure this out after what we've done with times of day. If the sun is here, I'll tackle this drawing right now. This side of the earth, the side opposite the sun, this should be dark. And the earth rotates around like this, counterclockwise, if we're looking at the North Pole. That means this person is at noon. This person is in the sunniest side part of the earth, right there next to the sun. So this is the one that shows a person at noon. In this picture, we have sun on the right. So the opposite side of the earth is dark. The earth's rotating like this. This person is right on the edge of the darkness, and they're going into the darkness, so this is sunset. Okay, so we got them labeled sunset and noon. Now it's only for this person. If the person was in a different place, like if this person was here, then they'd be at sunrise, or if this person was here, they'd be at sunset. Number 4, at which time of day do the sun's rays travel through more atmosphere? We've talked about this a little bit before too. If you look at the thickness of the atmosphere, it's the same, but because of the angle of these rays, it's going to be different. The sun's rays going from this person, from the sun to this person goes straight through the atmosphere. They enter the atmosphere there, they hit the person there, they go through that much atmosphere. Now the sun's rays that are traveling to this person, they're going to travel like that. They're going to enter the atmosphere here, and they're not going to hit the person until there. So they're going through a lot of atmosphere. So which time of day do they travel through more atmosphere? That would be sunset. At noon, the sun's rays travel through very little. So why does the sun turn red at sunset? it turns red because at sunset, when the rays are having to travel through a lot of atmosphere, there's a lot of stuff in the atmosphere. There are air molecules, there's dust, there's water vapor, there's all sorts of stuff. And only the rays that are best at penetrating that atmosphere can make it through. And going back to the previous page, the rays that are really short wavelength, they don't make it through very well. The waves that are medium wavelength, they don't make it through. The ones that are longest wavelength, those are the ones that make it through. So at sunset, the blue end of the spectrum does not make it to the person, the red end does. So these are the waves that that person actually sees. The rest of these get scattered all through the sky. So why does the sun turn red at sunset? It's because only the longest visible wavelengths, and I'm going to put in parentheses red light, can penetrate the thicker atmosphere. Again, I wrote only the longest visible wavelengths, which means red light, can penetrate the thicker atmosphere. And this is not really correct. It's not really that the atmosphere is thicker, it's just that the rays travel through a greater amount. So they travel through a greater thickness, even though the thickness is still the same. But I think that's an easier way to write it than the alternative. Okay. Next part, refraction or bending of light. And let me just show you this picture first. This is a picture of a prism, and typically prisms are triangular pieces of glass. They're triangular on the end. If you looked at it from the side, it might be a rectangle. So they're often like, let me put this back into place and I could draw another sketch. They're often shaped like this. From both ends, this thing would appear to be a triangle. So this picture, we're just looking at the end of it. Notice how white light is going in and then a rainbow of colors is going out. On the other hand, we can't really tell. Maybe a rainbow of colors is going in and white light is coming out. It doesn't matter. It could actually happen either way. And we're going to get to why and how it happens. So it begins with the speed of light. The speed of light in a vacuum, meaning the speed of light just out in empty space, is 650 million miles per hour, or about 300 million meters per second. And in a vacuum, there are no molecules with which photons of light can collide. So I've drawn light as a wave. Remember, it's also kind of a particle. Don't get too hung up in that. Just know that light is kind of weird. Now, the importance of what I'm about to show you is just to show you that light doesn't always travel 650 million miles per hour. That's its speed in a vacuum. When it's traveling through air, it travels a little slower, and here's why. So this is empty space. This is traveling through air. When a photon hits a molecule, that molecule can take in the photon's energy and then give off another photon. So it's like the Pony Express. So the rider rides from the light to a molecule, then he changes horses, rides another horse, changes horses, rides another horse. So every time a photon hits a molecule, the molecule starts to vibrate. It kicks out another photon of light, which hits another molecule, which kicks out another one. And that changing horses thing right there, that takes time. The light is going 650 million miles per hour between molecules, but to hit one and then get passed on to the next gap takes some time. And I'm not going to read all this because that's what it said. So it says, do you think light travels faster through a vacuum or through a solid? Well, it travels faster through a vacuum, empty space, because it doesn't have all these things in there to slow it down. In general, do you think light travels better through dense things or things that are less dense? Well, if you had light traveling through some air where the molecules were spaced like this, that would be one density. and then spacing like that, that'd be another density. Light's going to go slower through that. It's going to go faster through this. It's going to pass right through. So the answer is travels faster through things that are less dense. Now, back to one of the previous pages. This, I think people are familiar with light reflecting. That's what happens with, that's why you can see this paper. The light's hitting this paper, it's reflecting, it's going into the camera and doing some other stuff. And when you look at a mirror, the light reflects off. And I've explained that this scattering, that's blue light gets scattered all through the sky. But then this, labeled A right here, this refraction, this is what we're going to talk about now, the bending of light, why it bends. And that's what's being shown there. And you can see that not every color is bent the same amount. I should say at this point that a few of these things that I'm telling you may not be, I'm explaining things so that you can remember them. I may not be giving you the reasons behind things all the time, but I'm at least explaining ways to remember things. So when I'm saying that I'm using the analogy of an arrow to explain that bluer light bounces around the atmosphere and redder light passes through. Exactly why that happens may be complicated, but if you think of it as a sprungy, that's not even a word, as a curvy arrow versus a straight arrow, you'll remember it and it'll make sense and it's good enough. So what I'm about to tell you is another way to understand this. As far as exactly why it happens, I don't know that it's a really great explanation, but to help you remember what happens, it is good. So, number 3, this is understanding refraction. Does a car travel faster on a smooth highway or a grassy surface? That's a no-brainer. It travels faster on a smooth highway. There's a point to all this. Number 4, the path of a car is shown below. As it hits the shoulder of the highway, which front tire will touch the grass first? So we're looking at this car. This is the grass, this is the highway. It's not on the grass yet. It's about to hit the grass, and the question is which front tire is going to hit it. Now, to really understand what I'm talking about when I say right and left, turn it so you imagine you're driving the car. We're in the car right now. We're going this way. And if you're driving like this, the tire that's going to hit the grass first is that one. That's the right front tire. So the answer is, which front tire? It's going to be the right one. When that happens, which front tire will begin to move more slowly? Well, when this car positions itself, I'm going to draw it a little farther forward like this, so that the right front tire is there, the left front tire is there. This tire that's in the grass, that's going to start to slow down. This tire is going to keep moving fast. So if this moves slowly and this moves fast, I'm going to use little arrows to represent what's going on here. This is going to go fast, that's going to go slowly. Maybe I shouldn't say what's going on yet. Which front tire is going to move more slowly? It's the right one. Is this going to cause the car to turn to its right or to its left? So this is getting stuck. This is still moving fast. That's going to make the car turn to the right. This is how bulldozers move. They move along like this on their 2 tracks, and then one track slows down while the other keeps moving, and the whole thing pivots to the right. And if they move forward right there and the left one stops, then the whole thing pivots to the left. So the one that stops, that's the direction it turns. If I want to turn my bulldozer to the left, I stop my left side. If I want to turn my bulldozer to the right, I stop my right side. Or even make it go backward, and then you can really turn. So this car is going to turn to the right. Draw an arrow to show the new path of the car. Well, it's going to go like that. Light waves are like that car. The light wave on the right is traveling from air into water. This is the air, this is the water. In which substance will it travel faster? Well, light travels really fast in empty space. The more dense something is, the slower it goes. The less dense stuff is what it travels through faster. So it's going to travel faster in air. It's going to travel more slowly in the water. Show how entering a more dense substance will affect the path of light. I'm going to make this light like a car, except I'm just going to draw it like a box, like that. So if this is a car, it's going that way, the right front tire is going to hit the water. And it's not going to go as fast through the water because water is more dense. So this side's going to get stuck, it's going to slow down, this side's going to go faster, it's going to turn the whole thing to the right again. So it's going to do exactly what this car did. So there, draw the new path. Got it. That's number 9. Number 10. Now we get into different kinds of cars, which is kind of like different colors. If you have a skinny car and a fat car, and they're both traveling the same speed, they're on the same road, this is the road, this is the grass, and both of their right front tires, I'll turn it like this, the right front tire of this, the right front tire of that, they're both going to hit the grass. The question is, which one will probably turn the most? Think about that. Skinny car hits, fat car hits, which one's going to turn the most? So here's how to think of it. When the skinny car hits, this tire is going to hit first. And because it's so skinny, pretty soon after this tire hits the grass and the car starts to turn, this tire is going to hit the grass. Now with the fat car, this tire hits the grass and it's so wide it's going to take a long time. It's going to spend a long time turning before that tire ever hits the grass. So this one is actually going to twist more and this one is going to twist less. So a skinnier car would turn less because the two tires are really close together and it would spend less time turning before both wheels have entered the grass. This one's going to twist more because it's so wide. So skinny car turns less, fat car turns more. Now if you had to pick one of these to be like a fat car and one of these to represent a skinny car, I bet I can guess which one you would say is the fat car. Most people would say, you know, this is a fat car, this is a skinny car, then this is like a fat car. A wave that's like that kind of looks fat, whereas one that's like this looks skinny. Maybe you don't think the way I do, but try to think that way because it works that way. So this is kind of like the fat car, and if this is like the fat car, it's going to bend the most. It's going to hit this and it's going to do a pretty sharp turn. This is like the skinny car, so it's going to hit this glass and it's not going to turn much, and this one's going to be kind of in between. Let me make that even more extreme. Make that go almost straight down. This one's going to turn a little bit. This one's going to barely turn at all. So which light waves would you expect to turn the most? Most, least. So the point of all this, just to recap, is that light is going to refract or bend as it passes from one medium to another, when it goes from something of one density to another density. And the bending of it is like the turning of a car. And as light slows down, it turns toward the substance that's slowing it down. It turns toward the more dense substance. So in this case, I've got white light going through a prism. Diagram shows white light hitting a prism. The prism causes the various wavelengths of light to bend. Some bend more than others, so a color spectrum is produced. Label the paths shown with the appropriate colors. Remember, Roy G. Biv, red has the longest wavelength, blue has the shortest. I should probably go back to this diagram. If we wanted to say one of these is red, one of these is green, and one of these is blue. Green is in the middle wavelength-wise, blue is the shortest wavelength, and red is the longest. Which one of these would be red? This is like red light. This is like blue light, and this is like green. So the one that turns the most is the blue. The shortest wavelength turns the most, it refracts the most. The longest wavelength turns the least. So if you have light going through here, every color is in white light. It hits the prism, and then the different colors start to bend. They bend once, they bend again, and then they come out. Where would the blue be? Would the blue be at the top, or would the blue be down here? And the answer is, blue is the shortest wavelength that bends the most, so the blue end of the spectrum is over here. This is the red end of the spectrum, green's kind of in the middle, and I'm just going to abbreviate all the names of the colors. Red, orange, yellow, green, blue, indigo, and violet. So Roy G. Biv. And that's what you see when you look at the picture of the prism here. It's white light going in, it bends once toward the glass, like a little car. The right tire hits first, turns toward the denser substance, and then when it comes out, turns again, same kind of way. The color that bends the sharpest, makes the sharpest turn, is the bluish end of the spectrum. The reddish end makes the least sharp turn, and then green is right in the middle. Let's see what the next slide is. Oh, raindrops. So flip to the next page. Boy, I don't know if I can get through this in time. Probably have to have another video. But let me at least do this. When light refracts, it turns toward or away from the denser medium. Let me go back to the car, or this. So when light is, it's in air, this is in glass, this is the more dense medium, and it's moving at kind of an angle, and when it gets to the glass, it's moving more directly into the glass. It's turning toward the glass. It's not glancing off of it, it's refracting toward it. So that's what happens there. The eyeball's looking at the fish. We better come back to this in a little while. So this concludes part 2, almost done.